Good morning, student. So today this is our third lecture on semiconductor, and today's topic of discussion is what? Intrinsic semiconductor. Actually, depending upon the electrical conductivity of a semiconductor or whether that semiconductor is in pure form or some impurity atom is added to it, we are having two types of semiconductor. The first type of semiconductor is intrinsic semiconductor. Now, which semiconductors are called intrinsic semiconductor? Any pure semiconductor are called intrinsic semiconductor. Means a semiconductor to which some impurity atoms were added, those semiconductors they are called as what? Extrinsic semiconductor. Means semiconductor there are two different types. If semiconductor is in pure form, any pure semiconductor are called intrinsic semiconductor, and a semiconductor to which impurity atom may from fifth group of periodic table or few atoms may from third group of periodic table were added as an impurity. So any semiconductor which is doped with some impurity atom, they are called as extrinsic semiconductor. So first we will discuss what is intrinsic semiconductor. So what do you mean by intrinsic semiconductor? A pure semiconductor, any pure semiconductor. It may be a pure germanium. Most commonly used semiconductors are what? Germanium and silicon. They are called as a common semiconductor. So a pure germanium crystal or a pure silicon crystal, pure germanium or pure silicon, they are nothing but an intrinsic semiconductor. They are nothing but what? An intrinsic semiconductor. Remember, both germanium and silicon, they belongs to fourth group of periodic table. They belongs to what? Fourth group of periodic table. It means they are tetrahedral in structure. This is the tetrahedral structure. Their valency is 4. When I say that germanium or silicon, they belongs to fourth group of periodic table, and as far as silicon is concerned, what is the atomic number of silicon? Atomic number of silicon is 14. Atomic number of silicon is what? 14. It means the electronic configuration for silicon is 1s2, 2s2, 2p6, 3s2 and 3p2. Calculate here: 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 2, 14. So the electronic configuration for silicon is 1s2, 2s2, 2p6, 3s2 and 3p2. It means if I just look at the structure of atom of silicon, here is we are having the nucleus of silicon. Surrounding to nucleus, electrons are revolving in different circular orbit. In the innermost orbit, how many electrons should be there? They are 2 in number, 1s2. In the second orbit, there must be an electron corresponding to 2s2 and 2p6, 2s2 and 2p6. So in all 8 electrons are revolving in the second orbit. Now in the last orbit, outermost orbit, how many electrons were present? 2 plus 2, 3s2, 3p2. It means as the number of electron in the outermost orbit of silicon atom is 4, therefore we can say valency of silicon is 4. Valency of silicon is 4. So because germanium or silicon, they belongs to fourth group of periodic table, and due to this electronic configuration, the electrons in the outermost orbit of silicon atom, they are 4 in number, and those electrons which are lying in the outermost orbit, which are lying in what? The higher energy orbit, they are called as valence electron. So remember, the electrons in the outermost orbit of silicon, they do not satisfy the condition required for stable electronic configuration. Means if we are having a silicon atom with 4 electron in its outermost orbit, that silicon atom is not stable. That silicon atom is not stable. But we know that atom is the most stable particle in the universe. Atom is the most stable particle in the universe. So how every silicon atom will become stable? If I just look at the structure of silicon, remember silicon will exist in the form of crystal structure. In the nature, silicon exists in the form of what? The crystalline structure. So in the crystal of silicon, remember here I had shown the nucleus of silicon atom. As far as the centrally situated silicon atom is concerned, every silicon atom has 4 electrons in their outermost orbit. So each of the silicon atom will have only 4 electrons. For stable electronic configuration, every silicon atom needs 4 more electrons. Then only the electrons in the outermost orbit of silicon will becomes 8. And that silicon atom will becomes the most stable particle. So in order to have 8 electrons in the outermost orbit of every silicon atom will share 1 electron each from 4 of its neighboring germanium atom. Remember, silicon has a tetrahedral structure, means silicon atoms, 4 silicon atoms were present at the 4 corners of tetrahedral structure. So every silicon atom, it becomes stable by sharing 1 electron each from 4 of its neighboring germanium atom. Look at this. This silicon has 4 electrons in their outermost orbit. This silicon atom will have 4 electrons in their outermost orbit. Every silicon atom has 4 electrons. Now look at the atom which is at the center. It has already 4 electrons in its outermost orbit, and it will share 1 electron of this atom, 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 so that number of electrons in the outermost orbit of silicon, they becomes 8. And this happens with each and every silicon atom in its crystal structure. So every silicon atom, they become stable by sharing 1 electron each from 4 of its neighboring germanium atom. By sharing 1 electron each from 4 of its neighboring germanium atom, and at absolute 0 temperature. See here, this silicon atom is sharing 1 electron of this silicon atom, 1 electron of this silicon atom, 1 electron of this atom, 1 electron of this atom. So when a silicon atom shares 1 electron each from 4 of its neighboring germanium atom, so they are going to form what? They will form 4 strong covalent bond. So they are forming what? 4 strong covalent bond. Remember, at absolute 0 temperature, this is a crystal of silicon in which every silicon atom shares 1 electron each from 4 of its neighboring germanium atom just by forming 4 strong covalent bond. And when every silicon atom will form 4 strong covalent bond with 4 of its neighboring germanium atom, it means no valence electron is available for conduction of electricity. No valence, these are the valence electron. So at absolute 0 temperature, no valence electron is available for conduction of electricity, because each silicon atom, they will form strong covalent bond with 4 of its neighboring germanium atom. In other words, you can say, look at this. Here I had shown the energy level diagram of a semiconductor like silicon at absolute 0 temperature. We know whether it is a metal or whether it is an insulator or whether it is a semiconductor. As far as the energy level of electrons in semiconductors are concerned, it can be shown with the help of valence band and conduction band with certain gap in between them. This is a forbidden energy gap present between the valence band and that of a conduction band. So at absolute 0 temperature, no valence electron, valence electron means electron in the outermost orbit, no valence electron is made available, no valence electron is made available for the conduction of electricity, means all the valence electrons, they are available only in what? Valence band. No electron is free here for conduction of electricity. So at absolute zero temperature, as no electrons were made available for conduction of electricity, therefore you can draw the conclusion that semiconductors or intrinsic semiconductor, pure semiconductors, they behave like a perfect insulator at absolute zero temperature. What is the point that you have to remember? That the insulators, that is intrinsic semiconductors, at absolute zero temperature, they behave like a perfect insulator. They behave like a perfect insulator. Now at room temperature, what happens? At room temperature, as far as intrinsic semiconductors are concerned, these covalent bond will be broken. Few of the covalent bond, they will break down. Due to what? Due to thermal agitation. So at room temperature, due to thermal agitation, few of the covalent bonds will break down, few of the covalent bond will be broken, and few of the valence electron, here suppose due to thermal agitation, this covalent bond is broken, and these valence electron, they will receive thermal energy. And when electrons in the valence band receive the thermal energy, they will raise their energy to a higher energy level in a conduction band. Means this electron will reaches conduction band, will enter into conduction band and is now available for conduction of electricity. See here, few of the electrons, because at room temperature, out of strong covalent bond, few of the covalent bond will be broken. Greater the temperature, greater will be the number of covalent bond broken. Greater the increase in temperature of intrinsic semiconductor, means as the temperature of semiconductor goes on increases, number of covalent bonds broken will also increases, means a large number of valence electron, they receive thermal energy. And on receiving the thermal energy, electrons in the valence band, they will raise their energy to a higher level, means they reaches conduction band, and electrons are now available, free electrons are available for conduction of electricity. Means at room temperature, due to thermal agitation, when few of the covalent bonds were broken, few of the valence electrons, they receive the thermal energy. On receiving the thermal energy, there will be a rise in the energy level of free electron, and when free electron will reaches higher energy level, means they will lie in what? Conduction band, and electrons are available for conduction of electricity. Now look at this. Here purposely I have shown that electron at this place will enter into conduction band. These electrons, they reaches into what? The conduction band. And remember, when electrons from valence band enters into the conduction band, the place where valence electrons are there initially, at that place there will be a formation of positive charge called as a hole. In other words, you can say that at room temperature, due to thermal agitation, when electrons from valence band enters into what? The conduction band. So there is a vacancy of electrons in the valence band. Here these are that circle, these are representing what? Vacancy of electron. Electron at this place will enter into conduction band, electrons at this place will enter into what? Conduction band. This vacancy of electron in the conduction band is nothing but holes. They are called as what? Holes. Holes are actually effective positive charge. Holes are nothing but effective positive charge. So as far as intrinsic semiconductors are concerned, you remember 2 points, that at absolute zero temperature, it behaves like an insulator, while at room temperature, due to thermal agitation, few of the electrons from valence band can enter into what? A conduction band. And as far as that semiconductor is concerned, that semiconductor will acquire some electrical conductivity at room temperature, not so high, but it will have certain electrical conductivity at absolute zero temperature. Now look at this energy band structure of semiconductor. Whatever may be the number of electrons from valence band which enters into the region of conduction band, every electron will leave one hole at its place. In other words, if I say that NH represent number of holes per unit volume and Ne represent number of free electrons per unit volume. In an intrinsic semiconductor, if NH represent number density of hole and Ne represent number density of electron, means number of holes per unit volume or number of holes per cubic centimeter, Ne will represent number of free electrons per unit volume or number of free electrons per cubic meter. So in case of pure semiconductor, that is intrinsic semiconductor, NH must be equal to Ne. That is number density of hole is equal to number density of free electron or number of holes per unit volume or number of holes per cubic centimeter equal to number of free electrons per cubic centimeter. So this is about a pure semiconductor. Remember that as far as the electrical conductivity of an intrinsic semiconductor is concerned, as far as intrinsic semiconductors are concerned, the electrical conductivity of intrinsic semiconductor will be due to either due to positive charge carrier, that is hole, or it may be due to what? The negative charge carrier, that is free electrons. So through an intrinsic semiconductor, you may have the flow of electric current either due to flow of holes or due to what? Flow of free electrons. Means there are two charge carriers are there in an intrinsic semiconductor, and both of these charge carriers or any one of the charge carrier may contribute in the flow of electric current through it. And due to this property of an intrinsic semiconductor through which there might be a flow of electric current either due to flow of negative charge, that is free electron, or there might be a flow of electric current due to what? A positive charge, that is hole. So intrinsic semiconductor, they are having so many applications as far as designing of an electronic devices are concerned. Designing of an electronic devices are concerned. Now remember that as far as the electrical conductivity of a semiconductor is concerned, electrical conductivity of intrinsic semiconductor, it is very low at room temperature. The electrical conductivity of any intrinsic semiconductor at room temperature is very low. And if the electrical conductivity of intrinsic semiconductor is low, so that's why intrinsic semiconductors cannot be used in designing the semiconductor devices at room temperature. So by certain technique, anyhow we must have to increase the electrical conductivity of semiconductor. So the process of adding few amount of impurity atom to a pure semiconductor may increases its electrical conductivity appreciably. See what I am saying? That as far as pure semiconductors are concerned, to a pure semiconductor, a small amount of impurity atom, they might be impurity atom from 5th group of periodic table, they might be impurity atom from 3rd group of periodic table. So the process of adding pentavalent impurity atom or trivalent impurity atom to a pure semiconductor is called doping. It is called as what? Doping. What do you mean by a doping? Doping is the process of adding an impurity atom to a pure semiconductor, and addition of very small amount of impurity atom to a pure semiconductor may increases its electrical conductivity by very large amount. Remember that depending upon whether you were adding impurity from fifth group of periodic table or whether you were adding impurity from third group of periodic table, as far as this doping process is concerned or these impurity atoms are concerned, these impurity atoms, they are called dopant. What do you mean by dopant? Dopant means these are the impurity atom, small amount of impurity atom added to pure semiconductor. Small amount of impurity atom added to a pure semiconductor or added to an intrinsic semiconductor, they are called dopant. And the parent atom means maybe silicon or maybe germanium. The parent atoms, they are called as what? Host. Parent atoms, they are called as host. So you remember 3 points. Doping is the process of adding impurity atom to pure semiconductor is called doping. The impurity atom, the small amount of impurity atom which is added to what? A pure semiconductor is called dopant. The parent atom means pure semiconductor, that is silicon, it may be called as a host. Remember, as far as this dopant is concerned, if dopant belongs to fifth group of periodic table, that is when few atoms from fifth group of periodic table, they are added as an impurity. See here, if I just say that here we may have one of the atom from fifth group of periodic table, say phosphorus. If phosphorus is added, suppose here we are having an atom of phosphorus which is added as an impurity to a pure semiconductor, it means phosphorus is what? It is dopant. That phosphorus will acquire the position of one of the silicon atom, and we know that phosphorus has how many electrons in its outermost orbit? Phosphorus has 5 electrons in its outermost orbit. It means phosphorus will require only 3 electrons to become stable. But here phosphorus will share 1 electron each from 4 of its neighboring germanium atom. Already that phosphorus has how many electrons? Phosphorus has 5 electrons in its outermost orbit. Means here, after sharing 1 electron each from 4 of its neighboring germanium atom, how many electrons are there in the outermost orbit of phosphorus? These 8 electrons, they are just stable, that phosphorus atom, and we are still left with 1 electron free. Means every pentavalent impurity atom will donate, it will donate 1 free electron, and which is used for conduction of electricity. So when atoms from 5th group of periodic table will be added as an impurity, one of the phosphorus atom, when it is added to silicon, we know that phosphorus has what? 5 electrons in its outermost orbit because it is pentavalent. As it belongs to 5th group of periodic table, it means phosphorus is what? Pentavalent. It will share 1 electron each from 4 of its neighboring germanium atom. 4 of its neighboring germanium atom by forming 4 strong covalent bond. So, because phosphorus has 5 electrons in its outermost orbit, so that 5th electron of phosphorus is available as a free electron. Means to a pure semiconductor atom, depending upon how many number of pentavalent impurity atom is added, the number of free electrons available for conduction of electricity will be more or less. It will be more or it will be less. Remember that as far as doping process is concerned, when atoms belonging to fifth group of periodic table is added, and as that pentavalent impurity will donate one electron to a semiconductor, hence that type of impurity is called donor impurity. That type of impurity it is called as what? Donor impurity. Why it is called donor impurity? Because it will donate one electron as a free electron to a pure semiconductor. Now, suppose we are having an atom belonging to third group of periodic table, suppose boron. Atom belonging to what? Third group of periodic table, it may be a boron. Because boron, it is what? Trivalent. It belongs to third group of periodic table, means it is trivalent in nature. Trivalent means it has only 3 electrons in its outermost orbit. It will share 1 electron each from 4 of its neighboring germanium atom, and as far as the formation of fourth covalent bond is concerned, here there is an absence of electron, because this boron has 3 electrons. It will share 1 electron of this silicon atom, of this silicon atom, of this silicon atom, and forming 3 strong covalent bond. But in the formation of fourth covalent bond, because boron has only 3 electrons, it will share 1 of the electron of silicon, but here there is a vacancy of electron, or there is a deficiency of electron in the formation of fourth covalent bond, and this vacancy or deficiency of electron in the formation of valence band is called as presence of positive charge, known as hole. Means when one atom belonging to third group of periodic table, boron is what? Atom belonging to what? Third group of periodic table. So on adding a trivalent impurity like boron, that boron will take place of one of the silicon atom, that boron will share 1 electron each from 4 of its neighboring silicon atom, that boron will form 3 strong covalent bond with 3 of its neighboring silicon atom, while in the formation of fourth covalent bond, here we are having a deficiency of electron, and deficiency of electron, it means there will be a presence of hole. So presence of hole means it will accept the electron. So as this impurity atom, trivalent impurity atom, what is the trivalent impurity atom will do? Trivalent impurity atom will have an acceptance of an electron. Presence of hole means acceptance of an electron. So such type of impurity atoms, they are called as an acceptor impurity. They are called as what? An acceptor impurity. So remember that impurities are of 2 different types. It may be a donor impurity or it may be an acceptor impurity. Donor impurity means that impurity will belongs to what? Fifth group of periodic table, that is a pentavalent impurity. Acceptor impurity means that impurity belongs to what? Third group of periodic table, that is trivalent impurity atom. Examples of trivalent impurity atom is what? Either it is boron or aluminium or indium. Boron, aluminium or indium. Boron, aluminium or indium. And as far as that acceptor type of impurity is concerned, it is phosphorus or it is arsenic or it is what? Antimony. Phosphorus, arsenic or antimony. These are donor impurities. They belongs to fifth group of periodic table. So you must remember the example that the atom belongs to fifth group of periodic table, that is phosphorus, arsenic, antimony. They are pentavalent impurity, and because they were donating 1 electron free or 1 of the free electron as a donation to a pure semiconductor. So that's why that impurity is called as donor impurity. Whereas when the impurity belonging to third group of periodic table were added, third group of periodic table means boron, aluminium or indium, as they are trivalent in nature, absence of electron is nothing but presence of hole. Presence of hole is nothing but acceptance of an electron. So such type of impurity were known as an acceptor impurity. Were known as what? An acceptor impurity. Remember that as far as dopant and host are concerned, there is a restriction. That as far as dopant is concerned, dopant means the impurity atom which were added to a pure semiconductor. Why we are adding impurity to a pure semiconductor? Because anyhow we want to increase the electrical conductivity of semiconductor. Electrical conductivity of semiconductor. So the atoms, impurity atoms which are added as an impurity, the impurity atoms added to what? A pure semiconductor are called dopant. Remember, while selecting the dopant, a precaution must be taken that dopant atom, its size, its electronic configuration, it should be such that it will not disturb the crystal structure of intrinsic semiconductor. It will not disturb the structure of host. Select the dopant of a proper size. The electronic configuration, it must be compatible. It must be compatible with what? Compatible with intrinsic semiconductor, so that dopant will not disturb the crystal structure of any intrinsic atom. Any intrinsic atom. Now remember that a germanium or silicon, these are the pure semiconductor or these are the intrinsic semiconductor. And whenever impurity atom were added either to a germanium or to a silicon, that intrinsic semiconductor, it gets converted into what? Extrinsic semiconductor. What do you mean by extrinsic semiconductor? A semiconductor in which few impurity atom will be added so that the electrical conductivity of semiconductor can be increased. So in order to increase the electrical conductivity of any semiconductor, whenever few atoms were added as an impurity, that impure semiconductor are called extrinsic semiconductor, while pure semiconductors, they are called as what? Intrinsic semiconductor. Remember, as far as these extrinsic semiconductors are concerned, suppose we are having a semiconductor silicon. To a pure semiconductor, that is a silicon, if few atoms from fifth group of periodic table, few atoms from fifth group of periodic table, say few atoms of phosphorus were added as an impurity to a pure silicon semiconductor, then we know that each atom of phosphorus, phosphorus belongs to fifth group of periodic table, means phosphorus is what? Pentavalent impurity. So every phosphorus atom will donate one electron. Will donate what? One free electron to a silicon, means it will donate free electron to a silicon. And as far as that doped silicon atom or doped silicon semiconductor is concerned, that doped silicon semiconductor, it has electron as free charge carriers. Majority charge carriers is electron. So we are having that type of semiconductor, we call it as N-type semiconductor. What do you mean by N-type semiconductor? Any pure semiconductor, if it is doped with pentavalent impurity, then the majority charge carrier of that semiconductor is electron, means the majority charge carrier of that doped silicon or germanium crystal is electron. Hence it is known as N-type, means negative type semiconductor. Whereas when silicon is doped with trivalent impurity, pure semiconductor, that is silicon, to a silicon when few atoms belonging to what? Third group of periodic table, that is trivalent impurity is added. Trivalent means it may be few atoms of boron. What is the function of trivalent impurity atom? In the formation of fourth covalent bond, there is a vacancy of electron. That vacancy of electron is nothing but presence of hole, and hole will accept the electron. So that type of impurity is called an acceptor impurity. So here, in case when semiconductor is doped with trivalent impurity, then holes are the majority charge carrier in the conduction of electricity. So that type of semiconductor, it is called as P type, means positive type of semiconductor. So whenever we talk about the extrinsic semiconductor, and if I say N type semiconductor, it means in that extrinsic semiconductor, electrons are the majority charge carriers which are responsible for conduction of electricity. And whenever we will say P type semiconductor, it means that in that semiconductor, holes are the majority charge carrier, means electric current flows due to the presence of positive charge carrier, So this is all about the intrinsic semiconductor. So you must remember the basic point that pure semiconductors are intrinsic semiconductor, and when some impurity atom, maybe from third or fifth group of periodic table, were added as an impurity to a pure semiconductor, that impure semiconductor is called extrinsic semiconductor or doped semiconductor. The process of adding impurity atom to a semiconductor is called doping. The impurity atom added to a semiconductor, they are called dopant. The parent atoms to which impurity atoms were added, they are called as what? Host. The size and the electronic configuration of dopant were selected in such a manner that it will not affect, it will not disturb the crystal structure of what? Intrinsic semiconductor. Depending upon whether the impurity from fifth group of periodic table were added or impurity from third group of periodic table were added, extrinsic semiconductor, there are two types. If impurity belongs to fifth group of periodic table, we will get N type of extrinsic semiconductor. If impurity belonging to third group of periodic table were added, we will get P type of semiconductor, where holes are, or the positive charges are, the charge carrier responsible for electrical conduction. Now let us look at how there will be a conduction of electric current through an intrinsic semiconductor. Here I have drawn a diagram where that intrinsic semiconductor, across the intrinsic semiconductor, we had connected a source of electromotive force. A battery is connected across intrinsic semiconductor. Now see here, at room temperature, we know that few of the covalent bonds, remember, as far as intrinsic semiconductors are concerned, at absolute zero temperature, all these four covalent bonds, they are strong. No electrons are available for conduction of electricity, means that intrinsic semiconductor, it behaves like what? An insulator. But at room temperature, what happens? Due to thermal agitation, few of the covalent bonds were broken, and when few of the covalent bonds were broken, then the valence electron, they will receive the thermal energy, and on receiving the thermal energy, their energy level will rise, and they enter into what? The conduction band. Means few electrons are available for conduction of electricity, or semiconductor will acquire small electrical conductivity at room temperature. We know that when electron from valence band enters into the conduction band, the place from where electron leaves the valence band, they will create a hole. Absence of electron in a valence band is nothing but presence of positive charge, that is called as holes. So here, in the structure of intrinsic semiconductor at room temperature, I had shown that from these covalent bonds, suppose these are the covalent bonds which are broken due to thermal agitation. When covalent bonds were broken, it means electrons in that bond, here that electron will be shown by means of what? A black circle. So these are the electrons which gains the thermal energy, and they will enter into what? Conduction band. They will enter into conduction band. So the place from where electrons are moving from valence band to conduction band, so there must be a formation of what? These are the place from where that electrons from valence band were enter into what? Conduction band. So here there must be a formation of what? Holes. When electron from this place will move, it means here there is vacancy of electron. Vacancy of electron is nothing but what? Formation of hole. So when an electric field is applied across a pure semiconductor or across an intrinsic semiconductor, because few of the covalent bonds were broken, a pair of hole and electrons were available due to thermal agitation, and see here, electrons which are being negatively charged particle, definitely they get attracted towards positive terminal of a battery, while the holes which are the positive charges, they get attracted towards what? Negative terminal of a battery. Means here we are having two types of charge carriers. Electrons which are negative charge carrier, they were participating in the production of electric current. Holes which are the positive charge carrier, they are also participating in the production of what? In the formation of electric current. So as far as intrinsic semiconductors are concerned, look at this. Electrons are moving in a direction opposite to that of direction of externally applied electric field. Electric field can be shown from positive towards negative terminal. Means electron must move in what? In a direction opposite to that of direction of electric field. This external electric field will also contribute as far as thermal energy of valence electrons are concerned. There will be a slight increase in thermal energy of valence electron due to application of what? An external electric field. So in short, you remember that as far as intrinsic semiconductors are concerned, it has an electrical conductivity due to two types of charge carrier. It may be what? A positive charge, that is holes, or it may be a charge carriers like free electrons which are negatively charged electrons, negatively charged particles.